Throughout history, the progression and advancement of society has trended towards ever-increasing energy consumption. The Industrial Revolution gave us our first proper taste of this, and in our modern age we use a lot of energy, water, and resources to power everything. But even if we achieve complete energy control over our home planet, would it be able to keep up with the needs of continued technological advancement and proliferation among the solar system? Well, there is a free, near unlimited source of energy hanging in the sky and dominating our system, and its power can indeed be harnessed through a Dyson Sphere. That is what I'm going to be exploring today. What is a Dyson Sphere? How would we construct one? And what might a society that has achieved complete energy control over a star look like? Get ready, maybe grab a drink and snack if you aren't already watching this while eating, because this is going to be a bit of a longer one. I've also included timestamps so you can hop around the various points of interest. Without further ado, let's get started. Firstly, what am I even talking about? Well, a Dyson Sphere is a theoretical megastructure first formalized by Freeman Dyson in the 1960s that will be able to capture, store, and harness the energy of a star. It is one of the main hallmarks and requirements of what's known as a Type 2 civilization, a civilization that has complete control of the energy output of its home star. For us, this will mean a potential energy generation capability of upwards of 3.85 times 10 to the 26 watts, or 385 yottawatts per second. For reference, global energy consumption in 2025 was only 592 exajoules per year, or 164,000 terawatt hours. The energy produced by the sun in a single second completely dwarfs our current energy consumption, which raises the question of why we'd want to build a Dyson Sphere in the first place. Well, I'd say that the fact that the sun dwarfs our current energy consumption is exactly the reason we want to build one in the first place. We'd only need to cover a small fraction of the sun to be able to meet our current energy consumption needs. This system could be scaled upwards to meet future long-term energy demands without fear of pollution or running out of resources in space. This doesn't mean it's a short-term project though. As we'll see throughout the video, the intense scale of logistics alone makes this a project on the scale of decades or centuries. It'll be a long time before any meaningful construction is possible, and even longer before we've come even close to fully utilizing the energy of our sun. However, that doesn't mean this isn't a topic worth discussing in depth now. Now, I must confess, this wouldn't be an actual sphere engulfing the sun. That'd be an incredibly technologically infeasible engineering project, both in terms of assembling it and maintenance, or even just simply storing and transmitting the power outward. As such, an actual Dyson Sphere would be more of what we call a Dyson swarm, a huge array of satellites placed in orbit around the sun. A design such as this has a lot of advantages over the traditionally imagined Dyson Spheres, beyond its obvious near impossible engineering tasks I just mentioned. Firstly, being made up of a bunch of individual objects, a Dyson swarm is a lot less fragile than a Dyson Sphere, as it is dispersed across such a wide system rather than being a single solid object around a star. This also makes it easier to construct, as each satellite or swarm object could be launched individually onto its own orbital plane, rather than trying to connect them all together. It also allows for easier maintenance and replacement, as each swarm object could be replaced individually. As for the design of the swarm objects themselves, I've actually seen a few different proposals. To start, this traditional approach of using photovoltaic solar panels on the satellites that could harvest the energy directly and then beam it to receiving stations across the solar system. Another alternative I've seen is instead having the swarm objects be giant mirrors that reflect sunlight to receiving stations that then convert it to power by using it to heat up. God damn it, we just invented boiling water again. Okay, to be fair, as we've seen, it's actually more using Stirling engines or some type of air and water cooling mechanism, but it's still way too close for comfort. Like, come on, it's the sun. Surely we can use it for something more advanced than heating up water and spinning a turbine. Alternatively, rather than just being power collecting satellites or light reflecting mirrors, the swarm could be combined with habitats like an O'Neill cylinder, each one powered by and able to sustain itself through the sun. This however does come with some issues, primarily of keeping track of the billions of habitats. Maintaining cohesion in a system like this would be close to impossible. However, that doesn't mean there wouldn't be some advantages to this design. For one, even if maintaining political and societal cohesion is basically impossible, such a design could accommodate a truly staggering amount of people, and if each habitat was designed to be mostly self-sustaining from the energy it harvested from the sun, it means humanity's populations could grow by leaps and bounds without concern, without ever having to leave the solar system. Then again, this in itself might not be good, because with potentially trillions of people, it'd be near impossible to predict the behavior of such a massive society. So maybe this isn't the route we take. Lastly, there's one more approach I want to look at, though it's definitely a lot more far-fetched than the previous two, that of the Matryoshka brain. Matryoshka brain would be a nestling of Dyson spheres together, like the Russian nesting dolls, that are able to harness the full energy output of a star to power a massive computational system. Being able to harness the processing power of a star would open up a wide array of possibilities, from simulating whole universes to creating virtual worlds and allowing for consciousness uploading. The scale of Matryoshka brains is on a whole other playing field, and they honestly deserve their own dedicated video. There are just so many interconnected factors, especially how they would interact with each other or with lower civilizations, or how Matryoshka brain civilization would operate is just way too much to cover here, so let me know if you'd like a dedicated video on the topic. Now, let's walk through how to build a Dyson Swarm from scratch. In this home video tutorial for a quick little project to start your new hobby in megastructural engineering. Okay, but for real, beyond just being an interesting topic in of itself, the main reason I'll be talking about how to construct a Dyson Swarm is because in order to conduct a proper materialist analysis about how it affects human civilization, it is necessary to understand how we might undertake such a project, and also just its sheer scale. For the sake of video length, I will be excluding swarm habitats or Matryoshka brains from this discussion, as they both honestly deserve their own dedicated videos. And I don't intend to spend too long talking about this, because I am many things, but an engineer is not one of them. If you want to learn more about the specifics, I've left my sources in the description for further reading. Now, the first step in construction is one you might not have thought of. It's deciding where to put the swarm in the first place. Where we put our swarm within our solar system will have massive implications about how we go about constructing it, where we can gather resources, and how many swarm objects we need to be deployed. Placing in the general orbital plane of the inner planet is ideal, as it will be close to home and allows us to use said planet's resources. Venus and Earth are both eliminated as good potential sites, as the high Venusian temperature and surface pressure makes construction and liftoff functionally impossible. And using Earth's resources would overstrain our already tenuous biosphere. That leaves us with two viable locations, near the Sun around Mercury, and toward the edge of the inner solar system near Mars. Placing it near Mercury has some noted advantages. Primarily, its close proximity to the Sun and lack of atmosphere means we will need less swarm objects overall and will have an easier time moving it from surface to orbit. However, this is also its biggest drawback, as Mercury is exposed to the highest level of solar radiation, and the lack of atmosphere leads to wild temperature variance that will put a lot of strain on any mining, construction, and launch equipment we send up. In addition, reaching Mercury has its own set of challenges, as the lack of atmosphere and difficulty in efficiently reaching the planet due to its orbital eccentricities leads to a high cost of fuel, making setting up proper infrastructure on Mercury incredibly difficult. That leaves us with Mars. While its further distance does mean less solar energy and thus requiring more swarm objects, it's more than made up for by the milder temperature fluctuations, which makes designing equipment to work on Mars easier, as well as the ease of reaching the planet, with an upward launch window roughly every 2 years. However, using the Mars as the main spot for resource extraction and production could hamper efforts to colonize and eventually terraform the planet. Meanwhile, Mercury's kind of just sitting there, so take your pick. Now that you've chosen your location, next is choosing your design and knowing what resources you need. To answer this, let's revisit the two designs proposed earlier: photovoltaic solar panels and reflective spacements. For traditional solar panels, the main resources you need are silicon, aluminum, carbon, and silver in order to make the wafers, both of which are relatively plentiful on both Mercury and Mars. However, due to the complicated process involved in making the types of solar cells we need, which I promise I definitely understand, you need an inert manufacturing atmosphere with noble gases, something that can't easily be achieved without the import of required gases. This makes it more difficult, but not necessarily impossible. In addition, the overall efficiency of solar panels drops slightly, as the panels need to be shielded from damages from things like micrometeoroids, which can be accomplished through glass on top of the panels. So let's look at the alternatives: putting giant reflective mirrors in space. The idea behind this one is actually very simple. Rather than harvesting the energy directly, the sunlight would be reflected down to ground-based receivers, where it can then be turned into useful energy. How's this done, you may ask? No, back! In all seriousness, like I mentioned earlier in the video, the designs I've seen don't actually involve boiling water, and thank God for that. Rather, the idea is to reflect the sunlight to specially designed concentrated solar power collectors, where it will then be captured either by ground-based solar panels or Stirling heat engines. Both of these designs have their merits, but for the sake of the video, neither design really matters too much, so again, pick whichever one you prefer. Now that you've picked your preferred design and planetary base, you can finally start constructing your swarm objects. Yay! The manufacturing of your chosen swarm objects is easy enough. You can do it through automated factories that utilize local resources for manufacturing. But how do we get it into space? Rockets, even freely reusable ones, will require too much fuel and infrastructure to exist on the scale we need. So instead, what we need are mass drivers, which use electromagnetic forces to accelerate our payload at such a speed that it could go straight to orbit with minimal adjustment. Speaking of that, now they're on their own orbital plane, let's make this power usable. Whether we use direct solar panels or convert the sunlight to energy through the esoteric, never done before magic of boiling water, there's still the issue of getting the power from our solar satellites or your planet-bound receiving stations to Earth, where the Dr. Pepper factories are. Now, we can't just build a long power line extending out from Earth, so we need to utilize wireless power transfer. In practice, what this means is beaming the power to receiving stations in Earth orbit, which then redirected down to Earth to account for adverse weather conditions. However, an issue that arises with space-based solar power in general is that a lot of the technology needed for it is pretty underdeveloped, including wireless power transfer, and the efficiency over interplanetary distances is untested, which leads us to a much bigger issue, actually going about this. Megastructural engineering on a stellar scale like this isn't just a simple hobby anyone can pick up, but instead it is only possible through the efforts of a whole society and, realistically, through all of Earth united as one. As the construction is done on another planet, it requires a lot of infrastructure and space that we currently just don't have. In order to be able to construct it, we need to be able to 1. Get all the materials necessary to set up a swarm object factory to our planet, ideally as cheaply and renewably as possible, potentially through a space elevator, if we ever manage to manufacture more than half a meter's worth of nanofibers. 2. Develop the technology needed to build a mass driver in order to launch the swarm objects precisely into their own orbital plane. 3. Design and put the infrastructure needed to transmit the power. And 4. Likely establish a permanent human presence in outer space to ensure we are able to easily perform the needed maintenance tasks. Which brings us right back around to the question of space law. You really can't escape it, huh? In addition, there's another issue, timescales. Even if everything was perfectly coordinated under one unified global entity, which is an incredibly hopeful assumption to make, this is a project on the order of hundreds of years at the very best. So it isn't a near-term project. But hypothetically, if achieved, what might society look like? Now, it would be a lie to say that, if achieved, the construction of a Dyson Sphere would be anything less than fundamentally civilization-defining. It would mark humanity as a Type 2 civilization and provide, on human timescales, a free, infinite, and inexhaustible source of energy. However, there are many ways in which the material conditions and history of its construction would influence how this civilization would develop. As such, to be able to understand a Type 2 civilization, we must have a solid framework by which to analyze its characteristics. For this, I'll be using a framework from a paper I've linked in the description. It provides 4 different scales by which to analyze Kardashev Type 1 and 2 civilizations. The classic energy consumption framework originally devised by Kardashev, information relating to the ability of a civilization to collect, store, and transfer information and data on a society-wide scale, construction ability in relation to megaprojects, and population trends. The reason it's important to look at it from this angle rather than just a classic scale is because just looking at theoretical energy consumption paints an incomplete picture. Energy consumption tells us nothing about what the society of the civilization looks like, and we're painting a too broad and speculative a stroke if we relied on it as our only evaluative metric. So then, what are the characteristics of Type 2 civilization? Firstly, most simply is energy consumption. Although the metrics are based upon a civilization's energy availability. Without energy, productive forces, being factories, infrastructure, tool, etc., cannot be expanded and developed. As mentioned in the beginning of the video, the energy output of our sun is 3.85 times 10 to the 26 watts per second, and even with current energy growth trends, it will likely be thousands of years before we even manage to scratch the threshold of a Type 2 civilization. However, energy consumption doesn't tell us the full picture. The second metric is informational capacity, which relates primarily to computational power available to a civilization. Computational capacity is in part tied to energy availability and has grown alongside our energy consumption. So, even if we hit a brick wall in computer technologies, with enough space and the power of the sun, anything is possible. Thirdly is construction abilities, referring broadly to both the logistical and infrastructural abilities of a civilization to construct stellar-scale megastructures. As discussed earlier, in constructing the Dyson Swarm, it's more than just having the technology, but also the long-term space-based infrastructure and access to resources. This is ultimately the primary contradiction that prevents humanity, or any hypothetical civilization, from achieving a Type 2 status. If a civilization can't achieve the technology needed for the general automated construction and maintenance of a Dyson Swarm, or if it doesn't have access to the physical material needed, i.e. just simply not enough materials available in its solar system, then it won't be able to reach a Type 2 status. The last factor that must be considered is population. More people means more workers and researchers, but also constrains construction and energy consumption needs. Even though Dyson Swarm construction needs to be mostly automated, this dynamic will still hold true. And regardless, understanding how population changes under qualitative shifting of society to Type 1 and 2 civilizations is important to understand. Primarily, the population dynamics are going to be limited by Earth's carrying capacity, the physical number of humans that can be comfortably supported on Earth. Greater population growth leads to greater demand for energy resources, which makes sustainability a big question. Current models predict our population will peak at around 10 billion by 2100, before slowly declining as a result of hopefully increased global development and sustainability, resulting in a lower need to have kids. As such, if a civilization wants to continue growing its population, it needs to shift outwards, settling the other planets in its system. A Type 2 civilization would, as a result, have a much greater carrying capacity, being able to use massive amounts of energy at its disposal to sustain a far greater number of people. It's likely such a society would have a population far larger than we can imagine, spread out over the vast distances of our solar system, which brings up the question of how such a society might operate. However, predicting what humanity might look like as a Type 2 civilization is incredibly difficult, and it is speculation on a future that is hundreds, if not thousands, of years in the future. But it is still worth speculating on, even if our predictions turn out to be wrong. Using the characteristics and variables laid out, know that a Type 2 civilization will 1. Have a Dyson Swarm able to collect and store the energy of its host star. 2. Have large-scale computing abilities, either through advances in computer technology and/or utilizing the energy of the sun to power large-scale computational facilities. 3. Have an established off-world presence for the logistics and maintenance of its Dyson Swarm, as well as to support its growing population that comes as a result of the energy abundance. However, to know more, we need to know the fundamental question of ownership in that society, namely, who owns the giant sun sphere. So, do we have anything in international law that would tell us about the legal status of a Dyson Swarm? Well, kinda. The closest we have to work with is the Outer Space Treaty of 1967, which states that space should be treated as a commons, not owned by any one nation. However, this was written before we landed on the moon or knew what the surface of Venus looked like. It doesn't have any details on even relatively near-term prospects like space mining, so it definitely doesn't have anything on something as far out as a Dyson Swarm. However, this isn't a video on spaceline. If you want to learn more about that, I made another video on it previously. So for our purposes, we'll just assume current law as good enough and treat the Dyson Swarm as a common. With that assumption, we can get a better idea of what society might look like. For one, it would almost certainly be a post-scarcity society, one where the scarcity of basic goods would be functionally non-existent. This is because with the vast amount of energy available, it would have no problem engaging in any project it desires, including providing for many more people than we could possibly imagine the necessities of life. But what would this mean for society? Would people become lazy and unengaged, having everything taken care of by robots and never having to do anything ever? Well, maybe. This is what's known as a post-discontent society, the dystopian foil to a post-scarcity society. It would be more, you get everything you ever want and we drug you so you have no reason to be upset, versus you receive your basic needs so you don't need to worry about survival and can explore your passions unhindered. It's a subtle but scary difference. However, I see no reason why a Type 2 civilization won't be equally is likely to develop into the latter, a society where people will be free to explore their creativity and passions without having to worry about trying to make money with their career, or worrying about access to food, housing, etc. So, is there any way of predicting which one we'd end up as? Not really. There are a lot of factors at play, technological development and material factors, as well as near-term existential threats like climate change, which shape what we as a society might value. Would we just want an escape, or would we want us to be able to build up something more? Though, I do also want to point out that you don't need a Dyson Sphere to be post-scarcity. A Type 1 civilization, one that has complete control over its home planet, would be enough. With Type 1, we would have enough energy to comfortably support everyone on Earth. However, the Type 2 civilization would extend this onto a much greater scale, being able to support an unfathomable amount of people. Before we conclude, there's one more thing I want to talk about. As y'all are likely to have noticed, this video and my analysis have been generally very anthropocentric, focusing primarily on human society, and that was by design. However, we should still give other hypothetical civilizations their time and their spotlight. This will likely be a full video at some point, but for now, this will have to do. First, it needs to be acknowledged that because humanity is the only civilizational reference frame we have, any analysis is going to be operating assumptions based on our own society, and that might not apply to all of them. However, it is reasonable to assume that the constraints laid out earlier were the same in regard to an extraterrestrial Type 2 civilization. Any other civilization that manages to build a Dyson swarm would likely have also settled the solar system. This allows for them not only to construct their swarm easier, but also expand their population. Also, the Kardashev scale was originally created within the context of SETI, with the scale created as a rough classification of different levels of extraterrestrial civilizations. As such, Dyson Spheres or other similar megastructures could serve as a civilizational indicator of their presence. However, we haven't detected any verifiable signs of current or former stellar scale engineering undertaken by said extraterrestrial civilizations. Now, we haven't been engaged in SETI for all that long in the grand scheme of things. It's very possible we just haven't been listening long enough. However, this might indicate that there are no Type 2 or higher civilizations within our galaxy. The construction of a Dyson Sphere represents more than just the culmination of society's technological abilities, but a fundamental shift in the civilization itself. Being able to harvest the energy of a star means no longer being constrained to the limits of its home planet, but instead is able to utilize the full potential of its resources and energy of its entire solar system. We cannot truly know what such a society will look like. We don't even know if it's inevitable or even fully technologically possible. However, for us, it is both closer and farther than we think. 1,000 years isn't that long in the grand scheme of things. And the choices we make now and how we choose to develop and govern space may very well be what determines if we make it to a civilization with dominance over its star. I apologize for this video taking so long to come out. My planned release date for the video ended up right when I had several writing projects for school due. However, now that I have more time to dedicate to this channel, I promise the next few videos won't take nearly as long. That's all for this time. If you found this interesting, please consider subscribing, and I'll see you all later. Bye!